organizers for asking me to give a talk here. Yeah, so I'll be talking about. So I am of course, mostly not working on quantum trajectories and other things. My main interest in quantum many-body system. But what I'll discuss is that how this kind of new ideas and of course the new platforms that are going to be available or are available can also lead to new ways of thinking about quantum many-body system in a regime which are different from what you can do in standard quantum many-body system in solid state. Okay, so just to set the stage, so let's say in quantum mechanics, of course, so since the work will relate to measurement, so just to set the stage, so you have, let's say, some superposed state, and when you measure the qubit, so then you find either 0 or 1 with probability half. Now, if you have an entangled state, just like this bell pair, and if you measure one of the qubits, so of course again you will find 0 or 1, and again with probability half, you collapse the state of this bell pair either to this 0 1 or 1 0. So the main message that I am going to take from here is that if you have a entangled state and if you do this kind of local measurements, then what it does is that it unentangles the state. Okay. So essentially, if you have an entangled state, it can modify this thing. So now you can take this through, and you ask that now let's say I have a infinite system in a thermodynamic limit. Of course, I cannot just do one measurement and ask this question that how this measurement is going to affect this thermodynamic system, but I can of course do extensive number of measurements, and I can do many times. And I can ask that whether I can change the nature of the many-body state. Okay, so one of the example which is quite popular and which yesterday also Stitodi was talking about is by doing this measurement, maybe extensive number of measurement many times, you can actually change the nature of entanglement of the many-body state. So if you had some entangled state, so essentially there are extensive number of bell pairs going out of this subsystem. Then if you do some local measurements, you can end up into changing the entanglement structure of the many-body state into something which has area law, essentially only some bell pairs across the boundary. Okay. So this I'll just mention, but so another thing you can think about is not exactly related to entanglement, but you can even ask questions that can you even change the nature of the phases, the standard phases that we talk in condensed matter system. For example, let's say you have a metal or insulators, can you, by doing measurement, can you make a metal insulator and insulator a metal, or even more interestingly, can you take a superconductor and turn into an insulator and vice versa? Okay, just by doing measurements. So, so this is the question that I will be talking about. But before that, just again very quickly. So the other one, that where you change the nature of entanglement structure of the many-body states is now quite popular, and huge number of works are coming out, and these are also relevant for many of this quantum computing platform, where you can use gates and measurements, and then by tuning the relative strength of this entangling gates, which are scrambling, and measure local measurements, you can actually induce very interesting dynamical transitions. So for example, in this kind of random circuits with random unitary gates and interrupted by measurements, you can go from, when the measurement rate is very small, p very small, you can go from a volume law entangled state for non-equilibrium steady state into some area law state as you increase the measurement rate. And indeed, this critical point, so you have a critical point, and the critical point has many interesting properties, and critical properties which are generally not observed in even standard critical points. Okay. However, I am not going to talk about this kind of thing today. What I am going to talk about is the other question, that can you actually change the nature of phases. And the phases, by here the phases I mean non-equilibrium steady state. So I will be taking some many-body system and we will be doing extensive number of measurements for a long time, and I will end up into some state. And then I will ask that let's say in the without the measurement, the model let's say allowed superconducting or insulating state. By doing measurements, can you change a superconductor into an insulator into a superconductor? Can you get effectively some superconductor at higher temperature than a normal state? Okay, so I will actually show that you can do that. Okay, with this type of thing. Okay, so this is the work that I am going to talk about. So if you are interested, you can find in this preprint, and this work is done by Punendu, UG student at ISC. So the system, the many-body system that I am going to talk about is a very paradigmatic system of quantum phase transition and also for quantum computing platforms, which is the systems of Josephson junction. So what you have here is this islands of sort of nano size, mesoscopic size island of superconducting metals, let's say aluminium, and then these are much below their mean field temperature. So they have a well-defined pairing here, and then they are coupled by some weak links, okay, some Josephson links. So as a result, the effective model, some simplified naive model would be having some quantum model where you have a Josephson coupling term. So these I and J denotes the lattice sites where you have the superconducting islands, and then they are coupled by this Josephson coupling term. So if you just had this term, this is a classical model, and then it will lead to a phase coherent state like a superconductor, let's say at 0 temperature. Okay. However, because you have finite number of Cooper pairs on these islands are not really infinite like a bulk superconductor. They are some finite size. You also have some charging energy, and Cooper pairs are charged. So this charging energy you have to pay if you have to define the phase of the island, right? So that will lead to a quantum fluctuations through this kind of commutation relation between phase and the number. And these two, the EC and the charging energy and J, can compete and lead to a phase transition. And in fact, this is of course a old experiments where they indeed observed, this is a old IBM experiments with aluminiums and weak links. You make the arrays of these Josephson junctions here in 2 dimension, and indeed what they saw that if you measure current through this network of Josephson junctions, depending on the parameters, this EG by EC, so when your EC is very large, you can get an insulating state where the resistance diverges at low temperature, approaching T going to 0, but as you change this, you can go into a superconducting state where the resistance becomes 0. Okay. So this is and you can compare it well with theory. So you can well describe these quantum phase transitions where you can see that there is a quantum phase transition at 0 temperature as a function of this ratio. Okay, and this is again described by this. Now theoretically, of course, depending on the dimension and all, you will use different types of techniques to solve this, and these are not like transverse field Ising model, although in some limit maybe you can map into some spin models. But in general, even in 1D, these models are not very easy to solve. So just to get an idea about the phase diagram, you can do either some kind of a mean field theory, but the purpose in which I am going to discuss here some other kind of variational approximation we are going to use. So let me just introduce this approximation. So the reason this model is difficult to solve is of course this interacting term, which is these Josephson terms, right, this cos theta I minus theta j. Now what you can do, so of course you don't know exactly how to solve this, but you know a related problem which you can solve, which is the harmonic model. So what you can do, you can approximate in this kind of variational theory, which is called self-consistent harmonic approximation. You can approximate this cosine theta minus theta j term by a harmonic quantity with a coefficient which is a variational parameter. Okay. So this variational parameter you obtain variationally by some minimization principle of free energy or the energy, and then you will get a expression which is the self-consistent expression of this object, which is nothing but the superfluid density of this Josephson junction array. So when the superfluid density is 0, then you have an insulating state or a normal state. When this is non-zero, then you have a superconducting state. And this stiffness depends on the stiffness to a self-consistency condition, because this phase correlator on the other side depends on the D. Okay, so that's your variational theory. So now, so I am going to add another ingredient and eventually going to consider the situations or the comparison with a case with measurements. But right now I am going to just discuss just a dissipative effect of dissipation. Dissipation meaning that the system is in thermal bath, and the thermal bath obeys fluctuation dissipation relations, standard things. And in this case, you can ask that what is the effect of dissipation on this Josephson junction? And this is of course a very well studied problem. There was some anomalous experiment long time ago in 86, where people found that if your dissipation is larger than certain value, then look like that the the superconductor insulator transition become insensitive to EJ by EC ratio. Okay, so this was kind of a weird observation because this transition is a thermodynamic transition, and here is a thermodynamic transition which was completely determined by dissipation. Okay, so generally you would think that the dissipation should not matter, but they found that dissipation is controlling the transition. So that led people to come up with some theories which may not be exactly describing those experiments, but nonetheless they are interesting theories. So what people did, namely Chakraborty, Kibelsens and other, what they looked into is a version of this Josephson junction model where you have the old Josephson junction, but now you immerse it in a bath of oscillators, and these oscillators are just some harmonic oscillators, some modes of this bath which are in thermal equilibrium at some temperature T, which could be 0, and you couple this bath in a certain way to the Josephson junction. The way you couple it through the phase difference. Okay, so you each Josephson link you have a phase difference. You couple the phase difference of this link to the position of these oscillators which are fluctuating variable. Now you can think about this phase difference as just the current. So essentially what you are doing, you are coupling the current on the Josephson link with some dissipative bath. Okay, so that's the way you are coupling this. And then what you can do, because this bath is a simple type, namely caldera-Leggett type bath, you can integrate out this bath degrees of freedom. You can obtain some effective action for this Josephson junction system, but now due to the bath you have some dissipation. Okay, so you have an additional term where there is a, so this beta is just the inverse temperature. The main important parameter here is this coefficient alpha, which is a dimensionless coefficient, and what you can show that in this simplified model, this coefficient is just given by 1 over the resistance of the normal state. Okay, so essentially this controls the dissipation in the system, namely the conductance, or 1 over resistance that controls the dissipation. And so you have a dissipative Josephson junction model. So now you can ask that what happens to the phase diagram in the model. So earlier we looked into a phase diagram where dissipation was 0. So as you increase the Josephson coupling to the charging energy, you went from a normal state, an insulator, to a superconductor. So now you see that when you introduce dissipation, something which looks bit counterintuitive happens. Namely, when you increase the dissipation, what you find that the superconducting state is becoming more stabilized. Namely, it is appearing at smaller values of J by EC. So this looks bit strange, right? Because generally you would think that dissipation will destroy superconductivity, but it doesn't. It actually enhances superconductivity. In fact, if you increase the dissipation by a large amount, what you find that beyond some critical value of dissipation, which is indicated by this dashed line, in fact, the transition doesn't at all depend on J by EC, it's just a vertical line, only depends on the dissipation strength. Okay? And in fact, and this is a zero temperature phase diagram, if you go to very large values of dissipation, essentially you always get a superconductor for any infinitesimal values of J. So dissipation here is actually stabilizing superconductivity, and why is that? So the way you can think about it, that because of this current coupling, so if you can think about that this bath degrees of freedom in some loose sense are doing some kind of measurement on the system, and they are trying to fix this phase difference, theta I minus theta j, because that's how they are coupled, right? Now of course, if they are doing measurement, this phase difference, they will fix it to a random value, but then the Josephson coupling also would like to align them. So with these two, eventually you get a phase coherent state. So that this is how dissipation can actually stabilize a superconducting state. Okay, so you can do calculations and confirm this. Now what I am going to discuss is a variant. So we are now going to throw out this thermal bath. So I will have an isolated Josephson junction array, but it will not be completely isolated because I will bring some measurement apparatus. I am going to do certain measurements, and let me discuss that what kind of measurements I am going to do. So I am going to do what are called continuous weak measurements, and then I will also add some feedback. I will discuss the model slowly. So this model actually is a quite standard model in this literature of quantum measurements. Initially was done for a single particle weakly measured by Krebs and Milburn. In some work we for measurement induced transition we generalize it to some anharmonic oscillators chain and studied some transitions. So now this type of model you can also use for this purpose, looking into the Josephson junction arrays. So let me just describe the model. Okay. So in this model now, again I have a Josephson junction array. For simplicity, I am taking a one-dimensional array. And what I am going to do is I am going to measure the phase difference, okay, using some apparatus. So the phase difference again is like the current through this Josephson junction link. So how I am going to measure this? So what I do is I bring another set of objects which are also quantum particles. You can think of them some quantum particle with position and momentum. And what you do is you have a time dependent Hamiltonian to start with, where you have the Josephson junction Hamiltonian, and then at regular interval of time tau, what you do is you couple each of the link to one independent detector, and this is the momentum of the detector. So the detector is a quantum particle, it has a position and momentum. So what you are doing, you are coupling the phase difference or the current to the momentum of each of the detectors which are staying at each of the link, and this regular interval of time n tau. Okay. So just to show what we are doing, so we are essentially coupling these Josephson junctions at regular interval of time t0, t1, t2 like that, tn minus 1, tn. Between these two coupling, system just evolve with this Josephson junction Hamiltonian. But at these times, they are getting coupled with these objects, this quantum particle. So this is not yet any measurement. I am just coupling and entangling the system with this quantum particle. And I am doing it as an interval of tau. So remember this object tau, okay, it will come back. So now what is the measurement? So the measurement protocol is this. So what you do is you, just before this coupling at time tn, n tau, just before that, slightly before that, what you do is you prepare your quantum detector which has a position and momentum into a Gaussian state like that, which is a width sigma. Okay, again remember this sigma, it will come back. So this is the width that you control with this parameter sigma. Now at time tn, as I said, that they get entangled with the Josephson junction, whatever state the Josephson junction is in, and then they get entangled. And at tn plus, what we do, we projectively measure this detector, not the Josephson junction, but the detectors. Okay, and I get some reading to projectively measure the position of this quantum particle. So I get reading of their positions. Okay, and this
Sumilan,
yes.
What is this xi?
Yeah, xi is just a notation I'm giving for the position of this detector. So it's like xp. So xi is like x, the position of this detector, and p is like conjugate momentum. I'm just calling it xi. Yeah, I'll show you what is the use of this width. So this is actually measure the weakness of the measurement. Okay, so you'll see that. Okay, so you do the projective measurements, and these projective measurements, as I said, done on each link at each instant of this interval of time n, right? So I'll have a quantum trajectory I'm making out of this measurement. I'm going to do it many times. So that is what defines you a quantum trajectory. Okay, so now I'm going to skip the details. So what you can show, that you can actually show that there is a certain evolution of this density matrix of the system, which is the Josephson junction. So this density matrix is the density matrix of the Josephson junction array. So I am only looking into the evolution of the density matrix of the Josephson junction array, and this density matrix is at time tn minus 1, and this depends on all the other measurements before that I have done, okay, starting with some initial state. So that's the density matrix. Now from tn minus 1, from that time step, if I go to tn, I do two things. As I said, what I do is I first apply a unitary evolution, which is with the Josephson junction evolution. Then at time tau, after this time tn minus 1, I am doing this measurement, and this measurement you can write, you can show the particular setup. This measurement operator or the Krauss operator exactly look like a Gaussian operator. Okay, and in the Gaussian operator, what appears is the system operator, which is this theta I minus theta j, which I am measuring, but also the reading. Okay, the reading that I got by doing the measurement. So that determines this Gaussian operator. Now, how this sigma comes? So let me answer Manas's question. So this sigma appears in the strength of this Gaussian operator. Okay, so it's like POVM, so essentially the strength of this positive operator value measure, and this is basically the measurement strength. Okay, so now before I go into that, let me tell. So if you just do this measurement, you can show, and I will show that the system will heat up to very high temperature. Okay, you will not be able to study anything. So to control it, what you have to do, you have to give some feedback, okay, to the system. So this feedback, what is this feedback? So you get the measurement result. Depending on the measurement result, you apply some kind of single qubit gate. In this language, it is like this type of gate. So you have the measurement result. Using the measurement result with a strength gamma, you apply some feedback, and I will show what is the role of this feedback. Okay. So it basically acts like a dissipation, as you will see. Okay, so this is the setup. So I have measurement and feedback, and I am now going to take this limit where this width of the Gaussian sigma I am going to take infinity. However, this interval of time that I am doing measurement I am going to take 0. Okay, but I am going to keep this ratio, this number, the product of them to be fixed. Okay, so so this is the continuous weak measurement limit. Okay, in this limit I will be able to write the dynamics as a continuous evolution. And in here what appears is the measurement strength delta. Actually it is delta inverse, which is the measurement strength. And I have another parameter which is the feedback gamma. So these are the two parameters which are going to control my phase diagram. This tau will drop out because I am going to take tau to 0. Okay. So it turns out for this limit you can write down a Schwinger-Keldy's path integral for this theory. However, you have to remember that this is a non-unitary field theory. So you have to do a bit carefully this kind of Schwinger-Keldy's, but you can write a path integral for many body path integral for this system in this limit. Let me just mention very quickly that you can also write more standard things with this. You can, the dynamics I showed can be also be written like a quantum state diffusion. Okay. So where you have the, if you are familiar, you will realize I am not going to go into the details of this term. So these are due to the measurements. However, here since I am applying a feedback, there is an effect of the feedback on this effective Hamiltonian, which will also appear on the Lindblad or the stochastic evolution. And if you look into, like Shomik was talking about, if you look into disorder trajectory average density matrix, then you can also write a Lindblad dynamics for this. Okay. So you can derive all this from this microscopic model that I mentioned. The main important thing is you have measurement and you have feedback, and these two are very essential for our discussion. Okay. Okay, but I am not going to use this language. I am going to use this path integral language, which are equivalent for what I am going to discuss. Okay, so you write a path integral. So the path integral that we write is for a particular quantum trajectory, meaning I can write a path integral keeping all the records of my measurements, and that defines some partition function, if you wish, for this non-equilibrium process, okay, or generating function. Now what is this generating function? So you can basically show this generating function is nothing but the Born probability of the trajectory. Okay, so the whole trajectory you are doing many measurements, so you will get each trajectory will have a Born probability, and this is this partition function. Okay, and for this partition function you have some action. Again, the details of the action doesn't matter, but the main point is in the action this measurement outcome will appear, and then it will appear here and here. So this trajectory information enters in this action. So you are writing action for this full trajectory. In principle you can study it, but it is very hard. We have not been able to study it yet for this interacting system. However, what we do, we look into the long time steady state which become independent of time, independent of the initial, assume that it is independent of initial density matrix. And what we do is that we apply this self-consistent harmonic approximation, which was applied for the Hamiltonian, which I mentioned earlier. Okay, so you can apply it for field theory also, the self-consistent harmonic approximation. All you do, you replace your Josephson coupling term that appeared here again with a variational term like this, which is a variational parameter d. Okay, and you can write down a variational self-consistent approximation. Now here you ask a question that this is a non-equilibrium evolution, I don't have a free energy, so what do I minimize? Okay, so it turns out what you minimize is the Born probability, you actually maximize the Born probability of a trajectory. So that's your variational principle for these quantum trajectories, that you try to find the trajectory which is maximizing your Born probability. So that's the variational principle. So the free energy can be given by just e to the power, so you can write the Born probability as e to the power something, and that's like effectively like a free energy. Okay, so that's so this is the generalization for non-equilibrium processes, and you can obtain the self-consistent condition. Again, you can write it all the details, but the main point is now you are looking into a steady state, and you can ask whether do I have a superconductor, namely is the superfluid stiffness, which is the stiffness of this term, is non-zero or zero. Okay, so that will detect whether the non-equilibrium steady state is a superconductor or an insulator or a normal state. Okay, so that's you study. And as I said that we are doing a trajectory average quantity, we have not yet figured out how to efficiently do each trajectory, which will be an interesting problem. So as a result, what we are doing can be equally described by this Lindblad evolution with the feedback that I mentioned to you earlier. Okay. The main point is that within this approximation, ultimately you get some effective action within the self-consistent harmonic approximation, effective action with some effective superfluid stiffness. And the important thing is that when you do the trajectory average, you get a standard causal structure of this action. So again, if you are not familiar with Keldy's, doesn't matter, but what appears in the action is some causal Green's function, okay, in Keldy's things, and it turns out here also you'll have a causal Green's function, and that is very good because then you can apply various properties of the causal Green's function. So let me show the phase diagram that you get through this, okay. So the phase diagram, what is plotted here again is J by EC, the Josephson coupling for this measured model, and the measurement strength. So what you first of all see that there is a very weird looking phase diagram. So this is normal state or insulating state. I'll go over this more slowly next slides, but essentially you get a superconductor to insulator transition. However, there is an interesting aspect of it, you can get a reentrant transition. Okay, so for very small measurement rate you can have an insulator, then you increase the measurement rate, you go to superconductor. So remember again, my intuition was that I am measuring theta I minus theta j, I should be able to stabilize my superconductor, just like I did it for the dissipative case. Is it true? It turns out that it is not entirely true. If you measure too much, then eventually actually it destroys the superconductor, even though I am measuring theta I minus theta j, right? So that intuition on the thermal equilibrium bath is not always true. Okay, so this is the first message from it. So there is a reentrant transition. Now the question is we want to compare. So essentially here also we have some kind of bath, but the bath is made out of the measurement apparatus, not like a thermal bath which is in a thermal equilibrium. So what we want to do, we want to compare the standard dissipative thermal bath with the measurement bath, and we want to ask, are these two baths same or different? Okay. So it turns out in this model you can do that. So here is a way to do that. So what you do for that, you look into this Green's function of this action in the effective harmonic approximation. And the main point of the Green's function is any causal Green's function, it has a Keldysh component and some retarded and advanced component like response function and correlation function. And as you know that if you have response and correlation function, which is a nice causal structure, by taking certain ratio of the correlation to response function, you can obtain the fluctuation dissipation relation. Okay. So here also you can compare this for the measurement case, and the same thing you can do for the dissipative case, and you can compare these two structures. So if you compare these two structures, then what you find that this feedback that I applied, gamma, is exactly the way it appears in the Green's function, exactly like the way dissipation appeared in my dissipative model. Okay, so they are equivalent. So that's why we are calling it dissipation. Okay. Second thing is, if you look at the fluctuation dissipation relation, so if you look in the dissipative thermal case, then the fluctuation relation has to be cot hyperbolic h bar omega by 2t. Okay, that you cannot change it because it's an equilibrium bath. It has to be satisfied. And if you expand it, it is some series. Okay, if you are at very high temperature, then only the first term contributes, which is the classical fluctuation dissipation. If you look here for the measured case, what you find that this also has a series, but only two terms. It truncates beyond that. First term you can identify exactly like the classical fluctuation dissipation. So you can compare the first term, some effective temperature appears here. Remember, I don't have any temperature for the measured system. The temperature entirely comes from measurement strength and feedback. Okay, and in fact it is inversely proportional to feedback. So if you had feedback equal to 0, the system will heat up to infinite temperature. So that's what I mentioned, that's why you need feedback. Okay. However, what you find that when you go to higher sort of effectively lower effective temperature, then this series doesn't match with the equilibrium case. So you can expect that when you go to lower effective temperature, these two systems will be very different. Okay, and that is what indeed I find. So let me skip this and discuss this phase diagram. So what I am again comparing is the equilibrium dissipative case and the measured case with measurement and feedback. So what is plotted here is the temperature, so on this axis, and the Josephson coupling by EC for the dissipative case. So as you see, at 0 temperature you have a quantum phase transition, so you have to go a certain value J over EC when you become insulator to superconductor. Now increase the temperature, you need a higher value of J to become from insulator to superconductor, so this line goes like that for the thermal case. Now what you see here, if you are at high temperature, high effective temperature, for the measured case you see similar feature, but unusually when you come to low effective temperature, what you find that at arbitrary low effective temperature this system is actually always insulator. Okay. So however, if you increase the temperature it becomes a superconductor, and eventually if you increase even more it will eventually become again insulator, but you have a weird situations where in terms of effective temperature you have a low temperature normal state and high temperature superconducting state. So this is happening again, this is you cannot do in equilibrium. This is happening because you can basically manipulate this fluctuation dissipation relation, which you cannot do in equilibrium because you are bound by standard fluctuation dissipation. So these are the things when you do quantum many body theory with this kind of computation platforms that you can achieve, okay, which you cannot otherwise achieve in solid state system. So this is sort of the main message of this. I think my time is almost up and I am almost done also. So let me just mention few more things. So this is sort of the main results, that you can manipulate the fluctuation dissipation and you can get non-equilibrium steady state transitions which you cannot get in equilibrium system. Okay. Okay. So we of course use this self-consistent harmonic approximation, but it turns out in certain limits we don't need to do it. You can almost solve this problem exactly, meaning we can ask that how good is this self-consistent harmonic approximation. So it turns out that if you go to high effective temperature, then you can derive effectively, again the details doesn't matter, you can show that the dynamics of the system is just described by Garden variety stochastic Langevin equation. Okay, and so if you have a stochastic Langevin equation, however with a effective temperature which has nothing to do with outside temperature, it is controlled by measurement rate. Okay, it's often called quantum heating. So essentially this quantum heating heats up the system, and at high temperature you will get essentially looks like completely like a thermal case, you cannot distinguish, and you will have the, if you are 2 dimension you will have BKT transitions and all these things in the system. Okay. However at low temperature it will be different. So we can also look into certain limit, for example very high measurement rate or very large feedback rate, also you can do certain kinds of renormalization of the theory. And what you can show again without doing self-consistent harmonic approximation, that you can obtain some effective Josephson coupling which goes to 0 at very high dissipation strength or measurement strength. That's what we found from the self-consistent harmonic approximation, that eventually if you do too much measurement it actually kills the superconductivity. Okay, and we can also do some renormalization group which also agrees with this self-consistent harmonic approximation. And you can show why it is so different from the dissipative case, from the flow of this RG. Okay, they are very different. They completely change because of this fluctuation dissipation relation. So, this is just to show that the results that we get are not restricted to self-consistent harmonic approximation. You can confirm them in different limits using more accurate calculations. Okay, so these are not just artifact of self-consistent harmonic approximation. Now last 1 minute or so, let me make some comments with some comparison with some earlier work, and very quickly. Basically stabilizing superconductivity in non-equilibrium steady state is not new, and this is of course this famous work by Peter Joller and Sebastian Diel, where in cold atom system they designed so basically they engineered a bath, Lindblad bath for a Bose-Hubbard model, which is related to the model we are studying in certain limit. And what they did is they manipulated in cold atom system and designed a certain kind of jump operators, which can actually, basically you can interpret this jump operator is like the current operator. Okay, that's what I discussed. And what they showed, that if you have a non-interacting limit, then in Lindblad you get a dark state, which is essentially the long time pure steady state of the Lindblad equation, and that dark state for the non-interacting case is just BC. Okay, so this is how in the non-equilibrium case you can get a density matrix, which is of course satisfied by this term, that this term gives it 0 because it's the eigenstate of the Hamiltonian, non-interacting Hamiltonian. However, this is also 0 because it's a dark state. When L acts on this BEC, it gives you 0. Okay, it's a null state of this jump operator. So what we are also doing, we are not doing this framework, but in the measurement, essentially what we are doing is also we are measuring this current, and that's why it is stabilizing the superconducting state. However, there is an important difference. In their case, the effective temperature was controlled by U. They didn't have a feedback, and they had some phase diagram. I'll just finish. So they had some phase diagram. Now the new thing here is with the feedback, what you can do, you can reach some regime which you could not reach in this system. Okay, so you can get basically this kind of re-entrant transition, and that is happening because you have this feedback. So with this feedback, you can have much more richer phase diagram than you could study in this earlier proposal. So with that, let me just summarize and end. So just again to tell it again. So we devised some model motivated by this dissipative phase transition, but these are not the standard dissipation. These are dissipation coming from the measurement apparatus. And the main thing you do is you could control the fluctuation dissipation relation, which you don't have much handle in the equilibrium case, and that can give you a completely different phase diagram. In fact, you can make a superconductor insulator and insulator superconductor by measurement. With that, thank you.
Thank you. Questions? Yeah, there's a mic somewhere.
Thank you, Professor Banerjee, for the talk. This is a dumb question. Just could you explain what is on the, so blue one is the insulator.
Yes.
What is the green?
What is the color?
Green and yellow one.
Yeah. So sorry, I should have said. So this color is the D, the superfluid density. So wherever the color is bright, it means that it has non-zero superfluid density. And where it's completely blue, it is 0. So you can actually show with numerical accuracy, it become non-zero along this line. Okay. So you can just focus on this phase diagram. So this is determined by from this order parameter, which is D. Okay. So that's just the color. Yeah.
So blue one is the insulator, you're saying?
Blue one is the insulator because blue means D, the superfluid stiffness is 0. Okay. Which is basically the penetration depth goes to infinity.
And can we find BEC on this phase diagram?
No, this is an interacting limit. So there is so the BEC limit of this will be when you if you put switch, but that's a classical limit for this model. If you put the EC to 0, the charging energy to 0, then you have a classical model that's like the in the Bose-Hubbard language, that's the non-interacting model. So there you will get BEC. But otherwise, what you are getting, I mean, you can interpret it as a BEC, but it's weakly mixed BEC. Okay.
Thanks.
Yeah.
Any other questions? Yeah, Srinath says that.
I had one question. This is regarding the fluctuation dissipation theorem.
I guess this is on Zoom. Just 1 second.
Yeah.
So can you?
Yes, I had a question regarding the fluctuation dissipation theorem part.
Yes.
Am I audible?
Yes.
Yes. So, I mean, conventionally, one assumes thermal equilibrium to be an ingredient in deriving the fluctuation dissipation theorem. So, I was just wondering, curious to find out how it's extended in this context when you're in a non-equilibrium state.
Can you see this slide?
Yes.
So fluctuation dissipation is modified in the sense, as I told, maybe a bit quickly. So in equilibrium, the quantum fluctuation dissipation is that you obtain this ratio, which is like correlation to response function, which will be Côte hyperbolic. And if you expand this, it's some infinite series where the temperature appears. You don't need to expand it, but this is for comparison. In this case, it turns out the fluctuation dissipation just 2 terms at any effective temperature. You can sort of think about the first 2 terms of this. So the way it is modified at high temperature, it is not modified. You can say they are basically same, the first term in the series. However, if you go to low effective temperature, then you start seeing there is a huge difference between this because this is an infinite series, whereas this is just one more term. So that's how the fluctuation dissipation relation is modified in this case.
Okay, I mean, my point was basically that one of the key ingredients for deriving the fluctuation dissipation theorem is thermal equilibrium.
Yes,
so here it's a sort of a different kind of
it's a steady state. So you are assuming a steady state, and in the steady state we have some correlation and response function. and you can get motivation from thermal equilibrium, and you say that I still define the ratio of correlation to response function, and what is the ratio. Okay, so it's in that way. So first of all, we have a steady state. It's not thermal state, but you can ask in the steady state, is there a fluctuation dissipation relation in the sense of the ratio of correlation to response, and that's the spirit in which it is defined.
Okay, thank you.
Okay, Srinath, please.
Yeah, so basically it is an insulator because let's say imagine that you have just this island, superconducting islands, but they are not connected, right? So then of course there will be no flow. Of course you have local islands, but they are not connected. Now you are coupling them with Josephson link, right? Now once effectively the quantum fluctuations kill the Josephson coupling, then there is, so we are assuming that there is no quasi-particle channel to conduct the electricity. So the only way it can conduct is supercurrent, and so when the supercurrent goes to zero, this becomes an insulator. You have to heat it up, one thing. So basically you have to, so here what you are assuming is that there is a BCS temperature which is much higher than the temperature I am talking about. So you have to go close to the mean field BCS temperature, then each island will start becoming non-superconducting, and then you will have quasi-particle tunneling, and then you will have the normal transport. Yeah.
Okay, any other questions? Otherwise, let's thank both speakers in the session.